Hello, my name is Igor Cadota, and I'm a postdoctoral research scientist at Columbia University. Today, we're going to talk about our paper, WiFresh, Age of Information from Theory to Implementation, which is joint work with Mohamed Shahir Haman and Professor Eitan Modian. Our work is motivated by emerging applications that rely on sharing time-sensitive information for monitoring and control. So here you can think, for instance, of a fleet of autonomous vehicles or a swarm of drones. And in those kind of applications, network congestion can lead to outdated information at the destination, which then could lead to system failures and safety risks. And to address this very important problem, we propose WiFresh, which is an unconventional architecture for wireless networks that is built upon years of theoretical research. WiFresh is designed to achieve near optimal information freshness in wireless networks of any size, even when the network is overloaded. In our paper, we propose two different implementations of WiFresh. The first one that is designed to run at the MAC layer of software-defined radios and is implemented using FPGAs, and a second alternative implementation that is designed to run at the application layer of Raspberry Pis and is implemented simply using Python. In the paper, we show that both implementations can achieve 2 orders of magnitude improvement in terms of information freshness in the network when we compare it with a standard Wi-Fi network. To keep the presentation short and simple, we focus on this large-scale monitoring system that runs over standard Wi-Fi. Then we're going to model information freshness in this network using this new metric called Age of Information. Then we're going to discuss how we implemented WiFresh, and we're going to evaluate WiFresh in this software-defined radio testbed. So let's start by describing the monitoring system. So here we have 4 mobile nodes moving with different velocities, generating position information and sending that position information to the access points, which then relays that information to a remote monitor. The remote monitor does not know the current position of the cars, which are here described in blue. However, the remote monitor has this last known position information, which is obtained from previously received packets. So the remote monitor has this last known position information, and associated with each last known position information, there is this position uncertainty that we're going to describe further in future slides. So now let's describe the system from the perspective of the communication network. So here we have car 4 generating position information with a rate lambda and placing those packets in a queue. Then car 4 transmits the head of line packets to the access point, and the access point relays that information to the remote monitor. Once this information reaches the remote monitor, the last known position information here is going to be updated, and the position uncertainty is going to be reduced. And the position uncertainty is reduced because now the position information at the destination is fresher. Now, if some time goes by and no other packet is transmitted, the position uncertainties are just increasing. And here we have a position information transmission from car 3, and then now the last one position information here is going to be updated, and the position uncertainty again is going to be reduced because the information is now fresher at the destination. So this is how this system evolves over time. And this system would work great if we had 4 or 5 cars in it. However, when we consider a large-scale system with tens of cars in it, then this system may break down. So let's consider this large-scale monitoring system using standard Wi-Fi. But really here, when I say Wi-Fi, I just mean any communication network that uses first-come, first-served queues at the sources, and that uses random access to send packets to the access point. And those are very common choices. So a first-come, first-served queue is a queue in which when the source generates a packet, this packet is placed at the back of the line. This means that the head of line packet is always going to be the oldest packets in the queue. And this is the definition of the first-come, first-served queue. And when I say random access, I just mean that whenever a source in the network has a packet to transmit, it's going to wait for a random period of time, and then it's going to transmit its packet. If this source is the only one to transmit a packet in the time in the future, then this transmission is successful. Otherwise, if by chance 2 or more sources choose the same time in the future to transmit a packet, they're going to end up transmitting simultaneously. So we're going to have a packet collision, and the access point won't be able to receive any of those 3 packets. So this is basically going to be a waste of resources. And it's easy to see that if you have a large-scale system, you have more nodes in your network, you're going to have a higher probability of a packet collision, or you're going to have more wasted resources. So you're going to have less transmission opportunities per source. And if you're having less transmission opportunities, but you're generating packets with the same rates, this will mean that the sources are going to have more packets in their queue. So the time to go from the source to the destination, in other words, the packet delay is going to increase. So if you think about this from the perspective of the remote monitor, when you scale the system, you're going to have less transmission opportunities per source. So you're going to receive less packets per source. And the packets that you receive, they're going to have a higher delay. So what this will lead to is it will lead to a remote monitor that has outdated information about the position of all cars in your network, which is the challenge that we would like to address. To address this challenge, we're going to propose WiFresh, which has two important differences. The first one is a last come, first served queue, and the second one is scheduled transmissions. So in a last come, first served queue, when a packet is generated at a source, this packet skips all packets in the queue and goes straight to the head of the line. So the head of line packet is always the freshest packet in the queue. So that's the first change. The second change is to avoid collisions by scheduling transmissions. So this is how this is going to work. The access point is going to run a scheduling policy. The scheduling policy is going to select one of the sources, and then the access point is going to send a polling packet to the selected source. The selected source is going to then fetch its head of line packet, which is the freshest one, and send that packet back to the access point, and the access point will relay that information to the remote monitor, and at the same time, the access point is going to update its belief about the network states, run the scheduling policy again, select the next source, and send the next polling packet. Notice that in this mechanism, in this architecture, there's no packet collisions, and the transmitted packets are always the freshest one. And in this way, we address both problems that we had with the standard Wi-Fi architecture. However, we introduced a new challenge here, which is how to design the optimal scheduling policy, how to design a scheduling policy that will select the appropriate source to send a data packet next. And this is the problem that we're going to discuss in this paper. Next, we're going to model information freshness in the network using this age of information metric. And to introduce age of information, I'm going to use this very simple system with one source, one queue, and a destination. I'm going to use this timeline here. So we're going to consider time divided into slots, and the blue arrows are going to represent the slots in which packets are generated at the source, and the orange arrows are going to be the slots in which packets are delivered to the destination. So here is the packet delay of the first packet, here's the packet delay of the second packet, and here's the inter-delivery time. Using those metrics, we want to characterize how old is the information from the perspective of the destination. And this is where information freshness really matters. So here we're going to plot age of information over time. And I'd like us to consider this moment. This is the moment in which the first packet is received at the destination. So at this moment, the information is as old as the information contained in this packet. And the information contained in this packet was generated Z1 slots ago. So the age of the information at this moment from the perspective of the destination is Z1 slots. And now if one slot goes by and the destination does not receive anything new, then the information just got older. It got one slot older. So the age of the information is going to grow from Z1 to Z1 plus 1, then Z1 plus 2, then Z1 plus 3, and so on, until the next packet is delivered. Once the next packet is delivered to the destination, then the age of information is updated to the packet delay, and then it's going to grow again. So this is why age of information has this sawtooth pattern that we always see in those papers. And if at time t prime here, the age information is 4 slots, this means that at time t prime, the information at the destination is 4 slots old. So to keep the information at the destination as fresh as possible is the same as keeping this curve as close to 0 as possible. And this is going to be the goal of our scheduling policy. So now let's describe the relationship between age information and position uncertainty. So here, consider this last known position information associated with card 3. And consider this age of information plots, which is associated with this piece of information here. So here's the age of information, and assume that at time t prime, the age of information here is given by delta. This means that from the perspective of the remote monitor, the destination, the last known position is delta slots old. So this means that this car has been moving around with velocity v3 for delta slots without the remote monitor knowing about it. So the position certainty associated with this car is going to be given by the length of this radius, which is the velocity times the age of information. So here we can clearly see the relationship between position certainty and age of information. And we can see that to minimize the position certainty in the network is the same as minimizing the age of information of the entire network, of all nodes in the network. And this is going to be the goal of our scheduling policy. So let's look at our network model. So here we have the n cars moving around with different velocities, generating position information and sending that position information to the queue, to the last come first served queue. Then the access point is going to run a scheduling policy, select one of the sources. That selected source is going to fetch its header line packet and transmit it back to the access point. And this transmission here is successful with probability P1, and with probability 1 minus P1, there's going to be a transmission error due to noise. So the wireless links here, they are all unreliable, and P represents the quality of the links. And once the access point receives that information, it's going to relay that information to the remote monitor, and the remote monitor is keeping track of the position of all cars. So the remote monitor is going to have one area information curve for each car. So this is the area information curve associated with the last known position of car 1. This is associated with car 2. This is associated with car n. And the scheduling policy is going to decide the next car to poll or the next source to poll based on all of this information. In particular, based on information about the current area information and based on the quality of the links. So for WiFresh, we adopted the max weight policy, the max weight transmission scheduling policy, which was developed in our prior work here. And we selected or we adopted this scheduling policy because it's low complexity, it's intuitive, and it also has performance guarantees in respect to how low we can keep the area information in the network. And if you're interested in how we develop those performance guarantees, I would encourage you to take a look at our paper. And this is how the max weight policy works. So in each time slot t, the max weight policy is going to select source I star with highest value of this index. And this index is actually very intuitive. The index is given by the quality of the links, the quality of the particular link times the area information squared. So as you can see here, the link, the max weight policy is going to prioritize sources with good quality of the links and with high area information, which makes sense. If a source has a high area information, I would like to select that source in order for that area information to drop. So this is how the max weight policy works. And next, we discuss the implementation and evaluation of WiFresh in a software-defined radio testbed. But before we do that, I would like to briefly discuss our contributions. So in the literature, there are a number of theoretical works that develop and analyze scheduling policies that attempt to minimize the area information in the network. However, this is the first work to actually implement an area information-based scheduling policy in a real wireless network and evaluate its performance in practice. So here is our testbed, and next we discuss the main challenges of implementing WiFresh in this testbed. And the main challenge is complexity. So WiFresh is making scheduling decisions in real time, and if scheduling decisions were made in the millisecond timescale, then this may hurt the performance of our network. So to achieve microsecond timescales, we actually had to implement WiFresh at the MAC layer using the FPGAs of those software-defined radios. And of course, this was a very challenging task. The next challenge was to go from theory to practice. So as we mentioned before, we adopted this max weight scheduling policy, which runs at the access point and assumes that we have knowledge of the quality of the links, and we have knowledge of the area information associated with the sources. And in practice, we see that this is not actually true. For the access point to have the quality of the links, it has to estimate those parameters. And for the access point to have knowledge of the access of the area information associated with each of the sources, we actually have to have clock synchronization. So those are the two challenges that we discuss in the paper. And the third challenge here is packet fragmentation. The next important challenge that we have is the barrier to adoption. As you're going to see in a few slides, WiFresh actually gives us a significant improvement in terms of information freshness. However, this comes with the cost of complexity. So to lower this barrier to adoption, we thought of an alternative implementation of WiFresh that does not change anything in lower layers of the communication stack. So basically, we have this Python program that can be installed in Raspberry Pis, for instance, and with no additional changes in lower layers of the communication stack. We just run this Python program, and the underlying Wi-Fi network would behave as if it were a WiFresh network. And if you're interested in this alternative implementation, I would kindly refer you to our paper. So here we have our software-defined radio testbed with 10 sources generating packets of 150 bytes and sending those packets to the access points. Each of those sources is generating packets with a frequency of lambda packets per second. And by increasing this frequency lambda, we're basically making the network more and more congested. So here we're going to have experiments that run for a total of 10 minutes. And in each of those experiments, we're going to measure the average area information of the following communication systems, which the most important ones are just WiFresh and standard Wi-Fi. So here we have a plot of area information measured in milliseconds and in log scale. And here we have lambda increasing. So here we have a network with a low traffic load and a network with a high traffic load, so a congested network. And when the network is congested, as you can see here, standard Wi-Fi has an area information of around 5 seconds, which would correspond to a position certainty of 5 meters if the cars were moving with a velocity of 1 meter per second. In contrast, WiFresh has an area information of around 10 milliseconds, which would give us a position certainty of 1 centimeter, which is an improvement of almost 600 times, which is a little bit too much before you actually see a video of this working in practice. So here we have the WiFresh network with 10 sources generating packets and sending those packets to the base station or the access points. And here we have the area of information versus time. So here is not the average area of information. This is the actual area of information of the 10 radios, one on top of the other. And here we can see that the average area of information is going to be around 10 milliseconds. And this is in contrast to Wi-Fi, And here again, we have age of information versus time. And here you can see that some radios actually have an age of information of 12 seconds, 6 seconds, 4 seconds, 2 seconds, and so on. And here, from this plot, it becomes evident the difference between WiFresh and Wi-Fi. So here, by looking at this plot, you can see that WiFresh is the only one in which a higher packet generation rate leads to better information freshness in the network. And WiFresh is the only one in which this happens. And this happens for WiFresh exactly because we have two things. First, the last come first served queue, and second, the polling multiple access mechanism. And because of this trend, we actually can conclude that WiFresh does not need congestion control, because the higher the packet generation rate at the sources, the better the information freshness in the network. So this is our last slide, in which we just show some points which are covered in the paper. And at this point, I would like to thank you for your time and attention.